Okay, here we go. So, as you can see, the title of this chapter in itself is fairly intimidating. Logarithmic, exponential, and other transcendental functions. Ooh. Today we're going to talk about the natural log. So you use the natural log a lot in pre-calculus. You may have even dealt with it in Algebra 2. I don't remember. It's been years since I taught Algebra 2. It doesn't matter. But one thing you never addressed was, where does the natural log come from? You just found this cute little button on your calculator. It did a bunch of magic where if you took like the natural log of 4, it would spit out some answer, etc., etc., etc. But what we didn't ever talk about is, where did this magical thing come from? With calculus, we can address that issue. But we're going to do that in a little bit. First, we're going to talk about objectives. Natural log function. We're going to review the pre-calculus properties of natural logs so that you remember how to do certain things with the log. We're going to talk about the number e, also a number that you probably have used before. You could probably even tell me what an estimate value of that is, but we're going to talk more in depth about where it comes from. And then we're going to do some derivatives. So we're shifting away from integrals into a combination of integrals and derivatives. Okay? So let's start with a simple problem. Please solve that problem. Nice differential. Definite integral. Should get a nice pretty answer there. Remember, when you take the definite integral, you get a numerical value. When you take an indefinite integral with no limits of integration, you get a function. This is a definite integral, so you should get a number. I'll give you a second to work, and I will stop talking. For those of you Zoomers at home, if you get an answer, just unmute and say, like, yo, I got it. Or for roomers, again, if you have an answer, just let us know so that we can talk about your answer and check to see if everybody else got the same answer. So again, when you get an answer, just unmute and let me know, or say something in the classroom if you get an answer.
I'm a little confused because 1 over x, like the negative, it's like x to the negative 1. When you take it, like for like the number in the front, like it's no solution.
What?
Well, like like you know how it's like 1 over 1 plus the number?
Yeah.
The 1 plus negative 1 is 0, so...
Madison, you win a prize for today. Good job. So you're saying there's no answer?
I don't know.
Did anybody else run into the same problem? Zoomers at home, same problem? Okay, Madison, thank you for being industrious enough to open your mouth. You could, if you tried to solve the problem and you listen to what she said, she has a perfect explanation. Okay, when you take the integral, okay, so what does that mean? Quick review. This would be the same thing as 1 to 4 of x to the negative 1 dx. Raise the power by 1, so we get x to the 0. That's not a problem, because what's x to the 0? 1. But you multiply by the... Oh, that's not good. Which is exactly what she was trying to say. So that causes a problem, no solution. But, and you knew there was a but coming, that answer doesn't make any sense. Why doesn't it make any sense? Well, that's a graph of 1 over x. It's part of the graph of 1 over x. And so what is this integral asking you to do? It's saying find the area under the curve from 1 to 4. Using my outstanding coloring technique, there should be an answer to that problem. Okay? So you understand the dichotomy here. This, from a mathematical standpoint, doesn't make any sense, as Madison told us. However, if you look at the picture, there should be a number there. We just don't know what it is. Okay? So you understand the problem. Zoomers at home, you understand the dilemma here? You guys? Okay. So how do we solve the problem? We cheat. And that's where the natural log function comes from. The definition of the natural log function is a function that allows you to do that integral. And I guarantee you've never talked about that before in, let's say, a pre-calc or an algebra 2 class. You just all of a sudden said, oh yeah, here's this ln thing, and let's go use that ln thing. And we'll do a bunch of calculations with it and do all that other fun stuff. But from calculus, we can see we know exactly what that thing is. We can't do the math to take the antiderivative of 1 over t, so we just change it and call it something else, and that is the natural log. Okay, so for instance, if we go back here, pull out your calculators and do the natural log of 4. Get a number? K numero?
1.38.
Okay, 1.38. So what does that mean? That means that this shaded region that I have here is 1.38. So try the natural log of 2. Well, before you do it, hold on, don't do it yet. If you do the natural log of 2, will it be bigger or smaller than 1.38? Smaller, right. So go ahead, do the natural log of 2.
0.696.
Good, 0.6 something or another, okay? So now we can start to equate what the natural log means with the calculus that we've done already. Okay. There's the graph of the natural log function. It's probably been a while since you've done it, but just to give you an idea of what it is. It's asymptotic to the y-axis, okay, meaning it never touches the y-axis. So for instance, on your calculator, do the natural log of 0, please. No solution, right? Now, why is that the case? Okay, let's go back to this definition again. If I want to find the area under the curve from 0 to 1, I can't ever get that area because this never hits the y-axis, okay, which is also why that doesn't work. You'll also notice there's no values on the left side. So if you take and this you probably remember from pre-calc. What's the natural log of -2? Go ahead. No solution, right? Okay, so anytime you're asked to take the natural log of 0 or natural log of a negative number, it's not going to work. And then we've got some calculus stuff in here. This function is continuous, it's always increasing, and it's concave down. And again, you wouldn't have talked about that in pre-calc because you had no idea what those things meant. The other thing to mention is that you'll notice it passes through the point 1, 0. That comes up every once in a while when we do some translation stuff. Okay, good. We're good? How we doing, kids? Okay, excellent. Okay, so some properties of natural logs. The natural log of a quotient is the difference of the natural logs. And this is going to start coming back to you because I know you've done this before. The natural log of something raised to a power. You can move the exponent out in front. Okay. Now, you got to be careful, though. There's a difference between this and this. Okay. This is just a natural log of x squared. You can't do anything to this. This one, however, you can take that and bring it out in front to get 2 times the natural log of x. Okay, so exponents can be moved out in front. I think I've got no, that's another division. Addition. So the natural log, for some reason I didn't include it here. The natural log of a times b is the same thing as the natural log of a plus the natural log of b. So division becomes subtraction, multiplication becomes addition. I'm sure it's going to pop up somewhere else in the slideshow. Oh, there it is. I knew I had it somewhere. So the natural log of 6x is the natural log of 6 plus the natural log of x. Okay. Again, pre-calc stuff, hopefully your teacher helped you with that last year and you actually learned that. Okay, the number E. Am I going too fast or are we good? Zoom? A little fast?
Yeah.
I can slow it down. Okay, we'll take a break for a second. So, the number E. I don't think you've ever talked about where E comes from, have you? No, but you used it before, right? You took the natural log E and all this other fun stuff. So I'm going to show you, this is a fairly nerdy thing, but it's Friday, so what the heck. So let's talk about E. Who's got a $20 bill? Anybody? Nobody has a $20? John, can I borrow your $20 bill?
Yeah.
This is more, Zoomers, this is more of a visual for them being in the room. You'll have to deal with it at home. Thank you very much. Okay, so if you take out your calculators, no, don't take out your calculators, just watch. This is a $20 bill. This is all, okay, so for those of you at home, I got that. Okay, there's a $20 bill. Question number 1. Who's on the $20 bill? Jackson. Good. John, do you happen to know what president he was?
Was he the 7th? Or was he the 9th?
He was the 7th.
Okay.
Okay, so this $20 bill will help you remember what E is equal to. First of all, that's a $20 bill. Jackson was the 7th president of the United States. John, do you happen to know what year he was elected?
Would that be like 1832?
Not bad. 1828. He ran for 2 terms. And then we do some origami. If you guys at home could see this, you'd be amazed at my geometry or origami skills. We fold this $20 bill. Come on. Big fat fingers trying to get this to work. Go. We fold this $20 bill into this. Can you see that? What is this? Don't tell me a football. What kind of triangle?
A right triangle.
What kind of right triangle?
Isosceles.
Isosceles right triangle, also known as, Hannah, did you say that? No, somebody else said it. Josie, was that you?
No.
45, 45, 90.
Let's go.
So 45, 90, 45, same thing. So now get out your calculators, find your E button, and press the E button, and you'll see you get that number. It won't take it all the way out that far, but that's a nerdalicious way to remember what E is. What we haven't addressed is where does E come from? Okay? So, E is a number, and so we're going backwards a little bit. And it's defined here, but let me explain it a little bit. I'm going to explain it by going back this way. Going way back. Here. Okay. So we found that the area under this curve out to 4 was about 1.38. And then we talked about 2 being 0.6 something or another. What E does, E comes about by doing this following thing. It starts at 1, and you move over to the point where you get an area, which would be about here, where the area of this region is equal to 1. Okay? So we went over a distance and found the area. This is saying, here's the area, how far do I have to go over? And the distance you have to go over there is this number E. Okay, come on. There we go. So the pink region on the slide is guaranteed to have an area of 1, because that's how we defined E as. Okay. And what you remember from pre-calculus is, what's the natural log of E? 1. Okay. by the way, what's the log base 7 of 7? 1, right? So if the logs match, remember from pre-calculus, I'm sure you remember that the natural log is the same thing as log base e. Okay, so it's going to give you this value of 1, and that's where e comes from. Okay, so that's two pretty big things because they're things, the natural log and e, that you've worked with quite a bit in mathematics, especially last year in pre-calc, but you never really knew where they came from. So it's kind of we do you a disservice by not explaining the origins of these things. We just say, here's a tool, go use it. Okay. Questions? We're good? Zoomers, any questions? We're okay? Am I slowing down? Are we good? Okay. So, there's a fancy definition, which we already knew. Okay, you stick an e in there. That's just like the other definition of the natural log, except we replace the x with an e, and now we know what the value is going to be equal to 1. Okay. If you don't believe me, you can take your calculator, take the natural log of e, and it will spit out the number 1. Sometimes it might not spit out exactly 1. It might spit out something like 0.00 or 0.99999 or 1.00 because the calculator is going about a different way to find that number. Okay. All right, so we did a little bit of this already, so just to make sure that you know how to use your calculator. However, I do want to talk about part C. Why is the natural log of 0.1 equal to a negative number? Good. Keep going. So?
So that since the natural log of e is 1, if there's a number less than that, it has to be negative.
Your statement is 100% true, but what you haven't answered is why. Can you, by the way, can you guys hear Hannah at home? No? Okay, I'll make her talk louder. Talk louder, Hannah.
I don't know.
Okay, good. She just fired off, I don't know. Anybody else? Anybody at home? Why is this answer negative other than that's what your calculator tells you? And you don't want to just be a lemming being led around by your calculator.
Isn't it because it's just below the x-axis? Like when you look at the graph of the, or is that just not apply here?
That doesn't apply here because we're not. That would be a very logical solution because that's how we get negative integrals when the area goes below the x-axis. To help, let's go back 1,000 steps again. Oh, no, we'll stop here. Okay, so we can use this graph. Why is this natural log, what was it, natural log of 0.1? Why is a natural log of 0.1 equal to a negative number?
Oh, isn't it because, like when you take the integral there, like the value on like the top of the interval term is 0.1 and the bottom is still going to be 1, so because you're going backwards, it's negative?
Outstanding. Everybody follow that? Okay. We defined the natural log as being, well, here, let me rewrite it. We defined the natural log of x as being the integral from 1 to x of 1 over t dt. So we've done it already. We plugged in 4, we plugged in 2, we plugged in a bunch of 32, and we got these values. And what Prasad just said is, okay, well, if I do this and I apply the theorem down here, then the natural log of 0.1 should be equal to the integral from 1 to 0.1 of 1 over t dt. And we learned a long time ago when we started integrals, the top limit of integration has to always be bigger than the bottom limit of integration. It's not. So how do we fix that? What he just mentioned is we can flip it and get it where it needs to be. Whoops. But you have to stick a minus sign in front of it. Okay, so that's the math aspect of it. The other way to think about it is if I go from 1 to the right, I'm going to get a positive value because I'm accumulating area to the right, whereas if I go backwards, it's going in the wrong direction. So to get it to go the other direction, I have to multiply by -1. Okay? So that means, if you pick up on what we're laying down here, if you take the natural log of a number between 1 and infinity, we'll get a positive value, so that's going to be positive. However, if you take a natural log between 1 and 0, that's going to be negative. And remember, we can't go to the left of 0 because there's no values there. And then, of course, it's worth mentioning, what's the natural log of 1?
Zero,
Why?
because you just add one, like
Yeah.
you're not remaining like.
Good. Yeah. You're going from 1 to 1, which gives you a value of 0. Or if you pick up your trusty calculator and take the natural log of 1, it'll spit out 0 too. But again, we don't want to be lemmings. We want to be able to think for ourselves. Okay, so we did that. We talked about that. So let's take a derivative. Okay, so as it said in the previous slide, which I went through quickly, there are two versions of this. I'm going to suggest that we just focus on this part of it. Okay? And there's a reason why. The reason being is that if you just work with that side, it'll cover all possible scenarios. Number one only accounts for if you have the natural log of some easy function. And I'm very seldom, if ever, just going to ask you what's a natural log, what's a derivative of the natural log of x. Okay, because that would be silly. But I am going to ask you for things like what is the natural log, the derivative of the natural log of x. Natural log of x squared, sorry. Okay, so that becomes a u. And what does this say? Well, it says the derivative of the natural log of a function is the derivative of the function over the function itself. You're going to hear this u prime over u from me so many times you're going to want to kill me. But it needs to get burned into your brain. Do I need to talk about where this came from? Okay, because remember, we defined the natural log as an integral of a function. And that function is 1 over t. So if I take the if I take the derivative of an integral, second fundamental theorem of calculus says they cancel each other out. Okay. So this is basically a chain rule. And if I do give you something as simple as the natural log of x, u prime is just 1, so we get 1 over x. Does this make sense? Yes? Yes? At home, does this make sense?
Mr. Reedy?
Yeah.
So the derivative of a natural log is equal to the derivative of u over u?
That's it. Yeah, the natural log magically goes away. Okay? For those of you who didn't hear it, Max just wanted clarification that the derivative of the natural log of something is the derivative of u over u. And yes, that is correct. Okay, and it'll become a little bit more clear. I've got some examples to show you what it looks like. Okay, KISS method again. Keep it simple, stupid. If you're taking the derivative of a natural log, u prime over u. How do you do this? U prime over u. What will I get for an answer? U prime over u. Over and over and over again. Okay, so obviously we're talking about the derivative of a natural log, so I'm going to give you the derivative of a natural log problem. U prime over u. What's u? 2x. Derivative of 2x is 2. So u prime over u, we get 2 over 2x, and if you're feeling saucy, 1 over x. Don't get this u confused with the u's from the u to u problems. Okay, it's a different technique here. We just happen to use the same variable. All right, try that one on your own. Simplify it as much as possible when you're done, please.
Mr. Reedy?
Yeah.
Can I have my $20?
Oh, yeah, sorry, John. I'll get it to you in a second. I got to commend you, John. I do this every year. You would not believe how many years people have left without their $20.
I almost forgot about it, and I was like,
If you don't remember now, here, you can keep it as a football. It's a little memento of our time together. Thank you for the loaner. Aaron, let's pick on you. What do you got for me?
I did not understand.
Ooh. Okay, so let's take it in steps. What's u?
X squared plus 1.
Good. What's the derivative of u? What's u prime?
2x.
Good. So put that all together, u prime over u. Okay, u prime over u again. You told me what u prime is. That's 2x. So put 2x over x squared plus 1. No simplifying here, obviously. Do not cancel those x's. Okay. So again, keep it simple and don't overthink this. Can it get more complicated? Of course it can. We can throw in a product rule. This is fun. Now, this is not the derivative of a natural log. This is the derivative of a function involving a natural log. So it has to be done as a product rule. The first times the derivative of the second plus the second times the derivative of the first. And we know what the derivative of a natural log of x is. That's 1 over x. So we get that along with the simplifying. So the way I do it, and I don't know if you care about this, but I don't worry about the natural log of x. I still do u prime over u in my head. But what's u prime for the natural log of x? Well, the u prime is just going to be 1, so I get 1 over the function, which is 1 over x. Okay. To me, that makes more sense than trying to memorize two different theorems and how they apply. Okay. Now we got some fun. So again, taking a function that involves the natural log of x. And this time it's a chain rule involving the natural log of x. So I have some function raised to the third power. You know how to take the derivative of something raised to the third power. Bring the 3 down, reduce it by 1. That's what happened here. And then chain on the derivative of the thing inside. And by now, hopefully you've picked up on the fact that the derivative of the natural log of x is just 1 over x. And so we get to that puppy. And no, that can't be simplified. Well, I shouldn't say that. No, I should say that. You can't simplify that. I was going to say bring the 2 out in front, but that would have been a major mistake because this is the natural log of x quantity squared. Is anybody completely lost? Is anybody partially lost? I must be doing an outstanding job. Allie, is that a thumbs up as you're good to go or you're partially lost?
I think partially lost.
Okay. So again, emphasizing the fact that whenever you're taking the derivative, you're going to come back to u prime over u. So of A, B, C, and D, which one of those is causing you the most issues?
I'm a little lost on D because I was like writing down what, and you were saying something and I didn't catch what you said, something about like chaining on, so I didn't really get it.
Gotcha.
So
Okay.
you can explain that part.
All right, so here, let me try this. If I give you this, whoops, you can take that derivative, right? Because that is bring the exponent down, reduce it by 1, and chain on the derivative of that function. Okay? So we're doing the same thing here. So instead of a 2x plus 1 now, I have the natural log of x. So I brought the exponent down and reduced it by 1. That takes care of that and that, of that function, regardless of what it is. And then I chain on the derivative of that function. And what...
Okay, I understand that.
Got it? Okay, good. Beautiful. Anybody else? Excellent. Now things are going to get ugly. So what I'd like to do is let's take a 5-minute break. During that 5 minutes, get up, stretch your legs, get a drink, get a snack, see how many of those weapons you can identify. We'll talk about it when we come back at 10:26. Okay, thank you. Let's mute them so they don't have to listen to us. Same applies for you guys. Go ahead and get up, stretch your legs, use the bathroom, go get a drink. Is it warm in here? Yeah? All right, I'm gonna bust the window open, even though it's 20 degrees out. It could just be because I'm excited about that.
Yeah.
If that happens.
I wrote one of my favorite apples in my class, but that's also because I don't really care about anything else.
I can't tell if I love or hate the class.
I hated the class, but it was
I think I
honestly.
hated it too.
I thought it was really difficult because she doesn't give you like an outline to follow. She just kind of like gives you a prompt. I use four. She just
I
gives
kinda
you a
do four.
prompt and it's like write it and like follow other
Yeah,
people's
but
work.
also that's kind of how writing goes. Like,
Yeah.
you should have, there's no like genuine structure you should follow because otherwise you're just copying everyone else and they just sound the same.
Well, see, that's what she does. She's like, okay, we're gonna practice, like, we're gonna
Oh, I know. That's why I just did a practice and then
Tone
completely go on a different path.
tone and style.
That's what you're supposed to do. It.
And so she's literally
So
like,
she's
okay,
telling us
copy
all
the
these rules to
exact
follow and we're not
structure
supposed to
you write.
follow?
Yes.
Essentially, it's
How
not
is
having
that
a good
helping
essay.
you?
Right.
That doesn't
That's what I
help
did.
you. That's copying
I'm
someone
not gonna lie.
else's work.
Also, I wrote all my essays the night before.
Me
I'm
too.
pretty sure that's what everyone's doing. I put
It
my
was
heart,
really bad idea, but I got all my.
She gives.
I put my heart and soul into my first essay and I got a C on it.
Really?
Yeah.
Wait, what was the definition essay?
There's this I believe essay.
Oh my god, my
This
I
what?
believe essay
What
was.
was that? What was that?
It's like that whole website where like all the people submitted their stories and we had to like,
Oh,
do it.
that essay.
Yeah, mine was on the funny
No,
topic.
the definition essay was good. It's a better essay. I like that one.
I like that
one's
one.
fun, yeah. There's also a
Wait,
bunch of like
Joey,
annoying
you were in
images.
our class, right? For physics core.
Yeah.
Okay, that's what I thought.
Wait, we were in the same period, right?
Yes.
Yeah, okay. You were in that class too?
Yeah.
Oh my god. Anyway.
I don't know anyone who's in my class.
Yeah, I don't really pay attention.
And I get so in zero, I'm the only girl that's coming in person.
I'm not a loser.
I thought I was.
Kev, you know any of those?
Good amount, yeah.
No? I mean, obviously you know Captain America's shield.
Yeah.
What else? What else you got?
Yeah.
Well, hold on, wait. Let's bring everybody back, because then we're gonna have to have the same discussion.
Okay.
So I was thinking.
Yeah, I was gonna make a purple shell too.
I feel like I recognize a lot of them, but I don't remember their names.
What's that?
I feel like I recognize a lot of them, but I don't know their names.
I was
Yeah.
walking in the day and I was in like right behind the because I'm running and I'm dying to keep like I'm so and this one
I mean, some of those are just generic weapons, like there's just a
They're not though. Every one of them is from somewhere.
the bomb.
I mean, I saw
It's just a bomb.
Yeah.
No, I think that's a what is the bomb? Some of them I don't remember. I think the bomb might be from Mario, like no, because like from Mario Kart.
Yeah.
Because I think that's the hammer from.
That's from mine.
It could be from Mario, or it could be from. Doesn't he have a hammer in Donkey Kong? Like when Donkey Kong, when he gets his special, he can pound on the crates, right, or the barrels.
What's the bomb left one? I feel like they're ready.
You want me to tell you, or
Yeah.
it's from Soul Calibur? All right, before we get started on this ugly thing called logarithmic differentiation, let's see if we can get a number of these things named. Cab, you're going to start.
Okay.
What do you got?
The top left one, are those Tetris pieces?
Those are Tetris pieces. Good. Keep going.
I don't know the next two, but there's a Pokeball.
Good.
Is that a batarang?
You bet it is.
Then the green one's the green shell from like Mario Kart.
Uh-huh. A little louder so they can hear you at home.
Okay, I don't know like the next couple, but there's the gauntlet, like Thanos' gauntlet, the glove.
Oh yeah, the Infinity Gauntlet. Good.
Under that, there's like the hammer from like Mario.
Yeah.
And then there's Thor's hammer, like something with an M.
Mjolnir.
Yeah.
Uh-huh.
Like the sword, the nunchucks, like all the stuff on the right, that's from like Teenage Mutant Ninja Turtles.
Well done.
The one under it is like Cloud's sword from Final Fantasy, right?
Nice. Final Fantasy VII.
There's lightsabers in there. Captain America's shield. There's a portal gun.
From Portal.
Yeah. And the Hylian shield, and then like Link's sword. I think that's it.
Okay. Anybody else? Go, Max.
Above the lightsabers, is that the assault rifle from Halo?
It is.
And then to the left of the lightsabers, is that a gravity gun? What is that?
Yes.
Yeah.
This is the gravity gun from Half-Life. Good.
And then to the right of the green shell, isn't that from GoldenEye?
It is. It's actually from James Bond. It's from the man with the golden gun.
Yeah.
Okay.
And then I don't know the other.
Anybody at home?
The Blades of Chaos, like kind of in the middle from God of War.
Well done.
I also see like the Green Lantern ring at the top. with,
You
like,
bet. Yep. Good.
Wait, is the ring?
Is that the Lord of the Rings ring too? Or?
It is not. It's actually a ring from Sonic the Hedgehog. I thought it was the One Ring, but the One Ring doesn't look anything like that.
There's also the gun from Men in Black right there.
Yep, good. That's the cricket from Men in Black. Very well done. Any others?
Is that the Ghostbuster thing?
That's a Ghostbusters power pack, correct? I don't know if you guys would...
Like Freddy Krueger's thing.
Very good. Freddy Krueger's claws. Excellent. I don't know if you guys would know a lot of the other ones.
Wait. Is that the Gunblade from Final Fantasy?
Yeah, this is from Final Fantasy VIII, the Gunblade. Good. And then Max and I talked about this earlier. That's from Soul Calibur. You guys might know this one. What game that's from? The Chainsaw Gun? Very good. Gears of War. And how about this one? I don't know if you're too young for this, but do you remember that show?
Is that from like, it's either He-Man or like the one with like the cats or whatever?
Yeah, it's Thundercats. Good.
Thundercats, yeah.
How about the twin guns here? No? Those are Lara Croft's guns from Tomb Raider.
What is that crowbar?
The crowbar? Oh, you should get the crowbar.
From Half-Life?
Yeah, Half-Life crowbar. It's the first weapon you get in Half-Life. The others I don't know if you would get. So, the samurai sword is... Go ahead.
Is that Indiana Jones's whip?
Oh, very good. Yeah.
And then like the little like knife at like the corner, is that like the one from like was it the Scorpion King or whatever it was where it's like they control the time there with like sand in it?
Prince of Persia. Very good. Let's see. I believe, I'm not 100% sure, but somebody mentioned it earlier, so I think that's supposed to be the gun from GoldenEye.
What is that gun to the left of the
This gun?
Yeah, that one.
I'm not 100% sure, but I think it's the gun from the movie Wanted, where they shoot around the corners. Katana's from Kill Bill 1 and 2. This is Aragorn's sword from Lord of the Rings. This is the chainsaw from The Evil Dead. This is the BFG from Doom. This, I think, is from Mortal Kombat. Who's the guy? Yeah, thank you. Get over here. That guy. This I'm sure you don't know. That's from No Country for Old Men. You should know this one, though, but you probably... Well, maybe you don't. That's from Star Trek. That's an original gun from Star Trek. Is that everything? Oh, this one? I'm not sure about. That might be He-Man. And then the other one we didn't talk about is, I'm not sure about that.
There's also that random shield.
Oh, yeah, the black shield and the green sword I'm not sure about.
In the bottom right gun.
Oh, that's from, I don't know. It looks like a Halo gun, but it's not. Okay, beautiful. Nice distraction. Let's move on. Because now we're going to get into some a new tool for taking derivatives. So I pretty much thought we were done. Well, you thought we were done with derivative techniques, but now I've got a new technique that's going to allow you to take derivatives for non-logarithmic functions. Okay, and this is fairly ugly, so I'm going to go very slow through it and help you out. Okay, so forget about the solution for a second. Just look at that function. What you should realize is that you have the ability to take the derivative of that function as is. The problem is it's a quotient rule with two chain rules involved in it, and it gets ugly. Therefore, we have a different technique, and it's called logarithmic differentiation, and it involves logs. The 3 steps are listed below. And once you get those copied down, I'll take you through it and show you how it works. Okay, we good? Yes? Yes? Second? Okay, that's okay. I'll get a drink. By the time I get back, we should be ready to rock. Okay. Here we go. All right. Take the natural log of both sides. Easy. Put an ln in front of it. We're going to leave the left side alone and work with the right side. Whoops, sorry. So natural log of y is equal to. One of the properties of natural log is that the natural log of a quotient is the difference of the natural logs. So hopefully you followed that. I skipped a step and put it. Wrote the square root as raising to the 1/2 power. Okay, and I'm going to make my life a little bit easier again by doing this. Questions so far? Zoomers, questions? Roomers, questions? No, we're good. Okay. Now, step 2 was, I don't remember. I do, I'm just playing. Step 2, apply logarithmic properties and differentiate implicitly. Now, why does it say differentiate implicitly? Because we have y's and x's involved. It doesn't matter what you're taking the derivative of a natural log of. It's always u prime over u, so this is a y. The derivative of the natural log of y would be y prime over y. The derivative of the function over itself. Okay. 2 times 1 over x minus 2. Derivative of x minus 2 is 1 over x minus 2. Minus 1/2 times 2x over x squared plus 1. Any problems there? Okay, and having done a number of these things, I will say the hard part is what comes next. And what comes next is being able to solve for y prime. This one's not so bad, but I'm going to clean it up a little bit first and then apply the last step. So those 2's cancel. And so y prime would be equal to 2 over x minus 2 minus x over x squared plus 1 times y. That's not so bad. Except, what's y?
The natural log of x minus 2 squared over the square root of x squared plus
Close. Just the x minus 2 squared. No natural log in front of it. We put that there, remember? So this is actually going to be x minus 2 squared over the square root of x squared plus 1. Could we do more with that? Oh yeah, for sure. We could find a common denominator. We could distribute that. I don't care right now. Right now I just want you to be able to get to that step. But the key part of this problem is you need to solve for y prime. That's what's going to give us our value for the derivative. Okay, so we go backwards. We did all that. Okay, take the natural log of both sides, use your logarithmic properties to simplify it, take the derivative of both sides, solve for y prime, and we get down to that monster. If we go back to the very first introduction to that problem, if you would do the problem as a quotient rule with chain rules, you would get the same answer. It might not look the same, but it would be the same answer, especially if you plugged in values into that function. This is just an easier way to take the derivative of big, scary functions. Now, how are you going to know if you're supposed to use logarithmic differentiation for big, scary functions? Because it will specifically tell you, use logarithmic differentiation to find the derivative of blah, blah, blah. Okay?
So do we need to, should we try and simplify that any further?
I
Is that
wouldn't.
the answer?
No, that would just give you a headache.
Okay,
Yeah.
good.
What about an absolute value? Well, the natural log of an absolute value isn't going to matter because we're going to always be focused on the right-hand side of the equation. So negative numbers are going to turn positive. Negative values are going to turn positive by the absolute value. So we still end up doing the same process. So that it seems silly, but the absolute value just magically disappears. This will become more relevant when we start going backwards. By backwards, I mean taking integrals. When we take integrals of natural log functions, we're going to have to talk about the absolute value. For here, it doesn't really matter. It just goes away. We still get u prime over u. And again, don't get this confused with that. Okay, make sure you're being careful with this. We care about this one. So again, this is kind of beating a dead horse here, but taking the natural log of cosine, the absolute value of cosine doesn't matter. It's just u prime over u. What's the derivative of cosine? Negative sign. Okay, u prime over u. Well done. Okay. Ooh, I threw that last step in there. If you're feeling fancies in your pantsies, you can notice that the sine over cosine is equal to tangent. And so if this were a problem, let's say in the textbook, they would probably take it all the way down to this step. I don't necessarily care. You could stop there. But if your answers don't match, you might realize you got to do a little bit of trigonomic manipulation. Trigonometric? Yeah, there we go. All right, we're done. Anybody get the joke?
Good one.
What is it?
Log.
What kind of logs? Those are natural logs, yes. Those aren't artificial logs, those are natural logs.